So we were talking on a previous page about how do you choose between median and mean? They're both measures of center, but when would one represent the data more than the other? That's what we'll talk about today in this module. So we have a choice between two measurements of center. One we call mean, which we call sometimes referred to as the average, and then the other is median, which is just the middle value. We can use median or we can use the mean. How do we decide which measurement to use? In these next examples, we learn that the shape of the distribution and the presence of outliers help us answer this question. Oh, and I meant to say that when I was a student and I was learning about the median, they said median is the middle value, right? Median. But in the last example on the previous video, we saw that there were an odd number of values, so there was a middle value. But when there's an even number, we'll talk more about this, but I imagine some people are thinking about this and wondering what the heck. If there are an even number of values, then we take the two middle values because there is no one middle value, there are two in the middle, and we average them and find their mean. So let's say, make up an example here. I mean, we'll see this again in the future. Example, if there were homework scores like 80, 87, or I should put them in order, huh? 83, 92, and 95, and 95 again, something like that, let's say. In that case, there's no middle value because there are 6 of them. So this would be the middle. There's no middle value. There's 2 in the middle. So what we do is we average the 2 in the middle. So we find the mean of the 2 middle values. And again, this is only if there are an even number of values you're looking at. So we haven't talked about that yet. Yeah, and then this page doesn't talk about it. For an even number of values. Yeah, in the previous example on the other video that we saw, there were an odd number of values, so this wasn't even an issue. But we would find the mean. Okay, so I'd do 83 is the leftmost middle value, and then 92 is the other one. To find their mean, I add them together and divide by the number of values, and I'm only looking at the mean of 2 of them. So I'm going to calculate that. I'm going to add 83 plus 92 and divide that by 2, and I get 82.5. So that would be your median, and that's why on the previous video, the previous page that we saw, they said that in that case we looked at before, the median was the middle value, and it happened to be a value that was in the list. But in this case, 82.5 is our median, but that wasn't even one of the values. So for median and mean, it's very likely that your median or your mean value isn't even one of your data values. So just don't be surprised if that happens, that's all. Anyway, sorry to go off on a caveat. What do we got? So like they said, if there's an outlier, what does that mean? So let's look at this example. Here are a bunch of data values over here, all between 70 and 100. And so it might be someone's grades, right? And then there's one outlier way over here at 0. So sometimes that happens when there's an exam, especially an online exam. A bunch of people take it, they do well, or they do okay, whatever, but there are some people that just forget about it and they don't show up, or they never take it for whatever reason. So that's probably what happened here. This outlier got a 0%. But everybody else passed, or yeah, it looks like 70% and higher. Both measures of center are in the B grade range, so they calculated between those, the median and the mean, 84.5 and 81.5. The median is a better summary of the student's homework scores. The outlier does not affect the median. So that's, I guess, the difference. If there's 1 or 2 outliers that are super far away from all the other data values, the mean will be dragged down by that outlier. It'll really reflect. And what if there are multiple zeros? If there was 2 0 homework scores or 3 0 homework scores, then the median would be a lot lower. And I think it would kind of represent the middle, but it would really be dragged down by those zeros, and it wouldn't really feel like it's the middle ground between all those higher homework scores. This makes sense because the median depends primarily on the order of the data. Median once you jump from 0, the lowest homework score, to the next highest homework score, 70, it doesn't really, that big jump doesn't really affect it. It just looks for the one right in the middle. Changing the lowest homework score does not affect the order of the scores, so the median is not affected by the value of this point. The mean is not a good summary of this student's homework scores. The outlier decreases the mean so that the mean is a bit too low to be a representative measure of this student's typical performance. This makes sense because we can calculate mean, and when we do, we first add all the scores together, then divide by the number of scores. Every score, therefore, affects the mean. But in this distribution above, there are 26 homework scores for the student. If the teacher made fewer homework assignments, a 0 would have a greater impact on the mean. So it kind of depends. Yeah, if there are a lot of data values here, I guess that one lower one at 0 wouldn't affect it too much, but if there were not that many homework scores and all of them were pretty high except for that one, then the mean would really reflect. Sometimes the mean's even right here, way out in left field, you know, somewhere between all the big group of higher scores and the one that was low. We can see this in the distribution below. This distribution only has 10 scores. The one grade of 0 moves the mean to the C grade range. Yeah, so it's in this case, the average would be lower than a C. Here we'll look at another example. What's it about? Skewed income. So in this example, we look at how skewedness in a data set affects the mean and the median. The following histogram shows the personal income of a large sample of individuals drawn from the U.S. Census data in the year 2000. Notice that it is strongly skewed to the right, which means that there are lots of values on the left, kind of the smaller values, but not a lot on the right. This type of skewness is often present in data sets of variables such as income. So notice the x-axis, so between, let's see, this bar, or this, yeah, that's the highest bar on the very left represents incomes between $0 and $20,000. So most of the people, oops, sorry, too many zeros. Most of the people in the U.S. make between $0 and $20,000, or at least the ones that answered the census. And then there were about half of those numbers that made between 20,000 and 40,000. And these values I'm just getting from down here on the x-axis. And then someone took all these values. There were, over 4,000 people that declared that their income was between 0 and 20,000. There were a little over 2,000 people that declared their income between 20,000 and 40,000. So someone took all these values for all these bars and found the mean and the median. So here they have the values down here. The mean is 24,000. 24,000. Okay, and then the median was 16,900. So which one do you think represents the data values more? I think it's kind of like those homework scores. That one homework score of 0 really skewed the data downward. I think in this case the mean is also skewed in this case because all these there's not that many higher values here. The 240,000 up at the highest number here. There aren't that many people that are in this area, but those numbers are so high that when you average all these people's incomes, there aren't that many large values, but the ones that are large kind of skew it. So the mean doesn't seem to represent the average very well because most people don't even make 24,000. They make less.
Are you talking to me?
Sorry about that. Anyway, so here again we see that the mean income does not represent the typical income for this sample very well. The small number of people with higher incomes increases the mean. So like we were talking about, the mean is too high to represent the large number of people making less than 20,000 a year. A small number of high incomes gives the misleading impression that the typical income in the sample is 24,000. So yeah, if you had just told someone, I took a poll of a bunch of people and it seems like their average or their mean income is 24,000, then you would think that there's a lot of people that have about that income. But really, there aren't that many people that have that income. The majority are in between 0 and 20,000. The small number of people with a higher income does not impact the median. So the median income of 16,900 better represents the typical income in this sample. So the point from this is use the mean as a measure of center only for distributions that are reasonably symmetric with a central peak. When outliers are present, the mean is not a good choice. So a lot of times with grades, homework and exams, mean is used, but once in a while, I guess for things outside of school and stuff like that, you'd probably want to use median for the most part. Use the median as a measure of center for all other cases. So that's probably right there is probably a good thing to write down, because that might be asked later on an exam or something. When would you use median versus mean? So Mean is good if it's very symmetric, not a lot of outliers. But if that's not the case, there are outliers, or it's not very symmetric, it's right-centered or left-centered, then I would use the median. So you probably see median used a lot more than the mean. Both of these examples also highlight another important principle: always plot the data. Because if you don't plot the data, you might not realize that it's left-centered or right-centered, or it's not symmetric, or there are lots of outliers. We need to use a graph to determine the shape of the distribution. By looking at the shape, we can determine which measures of center best describe the data.